Okay, I think we can start. Welcome everybody to today's class on 18S191, Computational Thinking. I'll stop sharing my screen. And we're very lucky today to have a special guest lecturer in today's class, and that's Huda Nassar, who is a former postdoc at Stanford and now working for relational AI. She's an amazing Julia coder and a winner of the Julia Community Prize. And without further ado, let me turn you over to Huda. So Huda, if you unmute your microphone, everybody will be able to hear you.
Yeah, hi everyone, and thank you, Alan, for inviting me to talk about two things I absolutely love, graphs and Julia. So it couldn't be a better mix. So let me take a second to figure this out here in sharing screen. Okay. Fun fact, if you ever tweet something right before a talk, just turn on Do Not Disturb. Okay. So share screen, share. Can everyone see my screen?
Looks good.
Yeah, perfect. Okay, so we have a lot to get through today. So I'm just going to go ahead and get started. And this Do Not Disturb button is not working here. Yeah, we have a lot to get through, and let's just go ahead and get started. So first off, what I plan to do over the next 25 to 30 minutes are three main things. Number one is we're going to talk about graphs, since again, this is the topic for today's lecture. So we'll just go over some basics and like fix our terminology and have the same vocabulary so that we can go on to the second and the third items. The second item is going to be viral infections, and that is very much inspired by COVID, which we are currently in. So I just have to say a disclaimer here, which is I'm not an epidemiologist, and everything we're going to do here is just from a kind of toyish example perspective, from a network science perspective. And then finally, we're going to do something really fun, and I really am looking forward to this part, which is we're going to build two networks very related to the Julia ecosystem. One of them is going to be about packages. And then the second one is going to be about Twitter data. So we're going to collect all the tweets from the Julia Lang hashtag and build a network among the people who continuously tweet about Julia Lang. So to go ahead and get started, we're just gonna fix some of the basics again. So first we are talking about graphs. So this is really the main thing we will start with. And very quickly and basically, and I know you have seen something very similar to this previously in the class, but let me just take maybe hopefully less than a minute to just fix the notation here if anyone new is joining us. So here on this talk today, actually Alan and David are actually sitting and also sitting and watching the lecture, and they are co-instructors of this class. So Alan and David actually form a network. This right here is really a network. So one thing we can do with this network is you can see there are two nodes, node 1 and node 2, and then there's an edge. We can actually immediately build a network in terms of an adjacency matrix and put that in numbers. So if I give Alan here a node and David here a node, again, Alan and David, I know that Alan and David know each other, so I will put 1 here and then 0 otherwise. So right away, I just want to make the point that matrices and graphs are very kind of, there's like a seamless interplay between them, and we'll see that more as we go on to talk about other things today. Similarly, we can, this is just a basic graph. We can build a much bigger graph. So let's say now I'm going to add myself. So now this is Alan, David, and maybe David and Alan, both of them know Grant. So I'm just going to add G here, but I don't know Grant. So I'm not going to add an edge between us. So now we immediately went to from 2 networks to 4 nodes graph. So 1, 1, 0, 0, and then Alan knows everyone here, and then
Huda, may I ask,
1.
Does the 0 mean I don't know myself?
Oh, good question. Okay, so let me David knows all these people, and 0, 0, 1. Yeah, great question. So you do know yourself, right? But usually when we're donating, giving this notation of 1 and 0, it's really essentially signifying interactions as well, not just knowing. So the fact that there's a 1 between Alan and David, there's possibly an interaction between you two. So usually that's one way to think about it. In some graphs, we actually do add self loops. Like if there's, in this case, we're doing a social network, but if there's some stationary distribution or some distribution we want to model where the distribution itself should allow us to stay in the same location, that is a possibility. But in general, we do avoid, we just like, if we're building a social network here, yes, you know each other, but you don't do transactions with each other, if I want to put it this way. So moving on, so now we've actually made a slightly bigger graph with a slightly bigger social network, actually, or a matrix. The one thing I want to introduce right away here is this concept of a degree sequence. So one thing we often are interested in seeing is a degree sequence of a graph, because it tells us sometimes kind of key deterministic factors about the graph. So for instance, here, Alan, the degree of Alan is 3 because Alan is connected to 3 people. So if I have Alan here on a graph and then David and Grant and Huda, so we have 3 and 2 and then node 0 and then 2 and 2. This is usually, this is a very toyish example of a degree sequence, but we will see later that sometimes we will describe a notion of parallel graphs or preferential attachment graphs, which have a parallel degree distribution. And usually when we see such type of degree distribution, it's kind of a interesting thing to know as we get started working on these things. Now, one more thing I want to talk about in terms of, again, like keeping this idea of introducing notation here. We've talked about nodes, we've talked about edges. Triangles is another notion. So this is one triangle. Triangle is a clique as well. So clique usually is a K. Clique is something where we have a graph of K nodes where all nodes are connected. An edge is also in that sense a clique. These are other terminologies that I just wanted to put out there because we will use them later on. This I have said that it's a matrix, but it's also called an adjacency matrix. Not also called, that's really what an adjacency matrix and a graph are kind of counterparts of the same thing. Now, the next thing I want to jump into right away here is after we've defined a couple of these terms. So I hope by now you know what a graph is: a node, edge, triangle, cliques, adjacency matrices, and degree sequences. Let's elaborate a little bit on what it means when I say a graph is a matrix and a matrix is a graph. So here, what I wanted to show is, for instance, let's bring back this matrix over here and place it here. And let's do the graph notation of things, and let's do the matrices notation of things. So let's call this matrix actually A. And let's say if we do a squared, which is a times a. I have already computed that, and I will just type it here. 3, 2, 1, 1, 2, 3, 1, 1, 1, 1, 1, 1, and then 2, 2, 2, 2. So this is really linear algebra, right? Like we just took a matrix and we multiplied it by itself. And then we got a matrix. But what does this matrix mean? Actually, this new matrix means that every number here signifies how many times I can have a path of length 2 from node I to node j. So for instance, if I go back to the graph over here and I want to see in how many ways can Alan go to Grant in 2 steps? With one hop, basically. As we look at the graph, we can immediately say there's one way, and then let's see, is there only one way? Yeah, there is only one way. So this is Alan, and this is Grant. So I was immediately able to verify if there's one way or if I missed other ways by immediately looking at this matrix, so Alan to Grant. Now you can see that Alan here has a 3, and what does the 3 mean? Actually, this 3 means that Alan can go from himself to himself by 3 different ways. This is the first way, this is the second way, let me use a different color here. This is the first way, second way, and third way. Another way to read this, actually, when we look at the diagonal over here is actually these diagonal entries are the degrees of each of these nodes. So this is one thing to realize. So again, matrix multiplication here was really matrix multiplication was really equivalent to counting paths of length 2. And similarly, if we go to A3, A4, and so on, we will be able to count lengths of size 3, lengths of size 4, and so on. The cool thing is, for instance, A3, which is usually, when you think of A3, you can think of a 3 length path, but also a triangle is a 3 length path. So if you go from a node A to node B to node C and then come back, this is a triangle. And the more you work on network science problems or graph problems, you will realize that triangles in networks are actually very interesting and can add a lot to algorithms when they are incorporated. So being able to count those triangles or like see those triangles from also a linear algebraic standpoint, that is also interesting. Okay, so moving on. So I hope by now I have convinced you that graphs and matrices are indeed very similar, and we can accomplish, say, graph path counting from a graph perspective and from a matrix perspective. All right, so what did I have here as well? Are we doing the time? Okay. So we are, okay. So very quickly as well, I just wanted to go back to the idea of degree sequences, again, which showed up in the A2 as well. And if we want to talk about degree sequences, one thing I wanted to mention is sometimes you are given a degree sequence and someone tells you like to come up with a graph. That's one, there's an algorithm to that. And I just wanted to share this kind of fun, kind of toyish example of this graph. Let me see if I have the, so yeah, this is like a really fun, I will hopefully put all of this information on GitHub once I'm done. But this is really a degree sequence. You have 2, 1, and 1, and then this game actually tells you to build a graph out of it. The fun thing about it is that the best way to do it is to apply this algorithm called Havel-Hakimi algorithm, which I won't go over, but I just wanted to mention it. Another way to for instance, if you want to work with graphs, you sometimes just want to generate some random graphs to play around with. And we will see that we actually will need to generate random graphs to play around with later in this talk. So I just want to introduce 2 main concepts, which are the Erdos Renyi model, and then the preferential attachment model. All right, so for the first one, the basic concept is for every time you're building a network between nodes 1, 2, 3 until node say 10, and node 1, 2, 3 until node 10, you say, well, I'm going to connect 1 and 2 by flipping a coin. You flip a coin and you initially start with a probability that say, if you are above a certain probability, you do put an edge. And if you are below a certain probability, you don't put an edge. And then you do the same thing for every other pattern. The preferential attachment model, which I briefly mentioned earlier, is this concept when we have, it actually does happen in social settings a lot. For instance, there would be a clique present somewhere and someone comes in, so there's a preferential attachment to attach to the highly established nodes right away in that clique. So the idea is usually the network starts with like some sort of a clique, maybe a triangle, maybe a little more. And then a new node comes in, and then the new node with some probability distribution picks, say, 2 people to connect to. And then maybe it connects to these 2 things. And then a new person comes in, and then they want to choose 2 people to connect to as well. But this time, again, the probability distribution is changing as we go on because a node that has a higher degree has a higher chance to be picked, and so on and so forth. And then the network gets picked. So for now, I know I'm already running out of time. So what I will do in the interest of time is I will basically just, let's do this. Okay, so we won't do everything, I guess. I'll post everything that I've prepared online, but we won't go over everything. Here, I just wanted to show some Julia code for how we could generate those Erdos-Renyi graphs or the preferential attachment graphs. And I do have a disclaimer here that these are not necessarily the best ways to do these things. I actually have better code for doing both of these models, but this is really just to see how the algorithm is immediately mapping out to the code. A very straightforward, simple way to do it here is to generate this random graph of just n by n numbers, which n is the number of nodes that you're interested in. And then because I wanted to generate an undirected graph here, maybe I should have named it underscore undirected. Because I wanted to make it undirected, I am only taking the upper triangular part and tossing a coin on just the upper triangular part. And for every coin tossed there, I'm comparing it to this probability that I'm starting with. And then I'm just taking the max between upper bound and lower bound, which, sorry, upper triangle and lower triangle, which is essentially going to map out into moving the upper triangular part to the lower triangular. And again, this is actually here, it's a Boolean, so it's a ones and zeros. So this is an undirected and unweighted graph. For preferential attachment, as I described, so the model would start with some sort of a clique. So here is where I'm building a clique. So I'm saying there are n0 numbers where that's going to be the beginning of the model, and that's going to form a clique. And then every single time a new node comes in, I'm just going to build a probability distribution, basically toss a coin k times because it's going to connect to k people. And then based on these probability distributions, I'm going to pick the next nodes to connect to. So this is where I'm picking the nodes to connect to every time a new I comes in from n0 to n0 plus 1 to n. So I will move on from here, and then I will, if you find me online, my GitHub handle is NASSARHUDA. I'll probably type it, write it here. You can find me and I'll post all of this code afterwards. Okay, so I think this was the first part. We are already out of time. The second, sorry, this was the first part. The second,
10 minutes or 15 minutes or so, it's fine. Just up to you.
Okay, if I want to go to like 3:10.
That's fine.
Okay. Okay. So for the viral infection part, I think I'm just going to talk about it for like maybe 5 minutes, because I know most of the resources I'm using are actually online and I will have references to them. So I think since the references are very good and they are available online, I might not spend too much time on it. Okay, so next part is viral infections. Okay, so viral infections. So I think what I had here is, let's see, if I added this. Okay, so here in this model, we have a graph and its corresponding adjacency matrix, which we already introduced, and now you know what that means. And for instance, if I look at a node here, say this node 4 over here, it's connected to 2, 3, and 8. You will look, if you actually look at 4, you will see that it's connected to 2, 3, and 8. So you're good. Okay, so what happens in this infection model? We're actually setting two main states. The two main states are infected or not infected. So probability, we will use probability of I infected at time t is equal to x at time t of node I. So we will build these vectors x at time t, which is usually will be these probabilities of every patient or every person node I in our network to be connected or not. And the way we will proceed next is really if we start with some infection model and like there's someone who is infected, we will just assume that the model will have some probability rho where if a person knows another person, there's a rho chance for them to be infected. Now, the significance of this rho is really dependent on, for instance, like now we know of these terms, social distancing and wearing a mask and so on and so forth. So this rho is usually related to how is the social network actually behaving. So because I don't want to spend way too much time on this, and because I know the resources are present online, I'm just going to run a couple of the visualizations and focus more on the Julia aspect of things here. So let me go to the viral spreading scenario. All right, so here, the main thing, okay, so first of all, I do post the two links where I'm using, like, this is actually written up notes, so like it's very clean and pretty. If you actually read the document, I do have the link to it here. The key thing that we're doing here, let me go to this evolve function. The key thing is that every time, okay, so let me actually take this back for a second. We use one interesting concept where, well, it's not super interesting. It's just we use it because we want to be able to use matrix algebra or graph algebra. So we have A times B times C. We know that that's equal to e to the log of A plus log of B plus log of C. And since we know that probability of I infected at time t is really equal to 1 minus not being infected. And not being infected is really essentially a summation over, sorry, it's not a summation. It's a multiplication over not being infected from every single neighbor. So if I have neighbors of I here, so 1 minus pj, j belonging to the neighbors. So we are multiplying over all of these neighbors. So the key component we want to do here is, since if we have an adjacency matrix, if we actually have a summation over neighbors, that is so easy to do in linear algebra and matrix multiplication. So we just do that instead. And that's really the key trick that we do here that allows us to run this infection model pretty fast. So with that, I think I will keep this part short since I know the references are there, and maybe just show you a couple of the visualizations that you can actually create with those. Let me see if I have them here. Okay, so this is one of the models where you can see how the spread is going through the network. And then the key thing here that I wanted to show is, I guess if you actually, oh, this doesn't. If you do end up minimizing this row value over here, where the chance of you interacting with someone, even though you're seeing them, even though there's a 1 between you and them, there is a connection, or you regularly see them, the spread of the virus will still be slower. And this will take so much more time than, for instance, its counterpart over here that will actually occur super quickly. Okay, so now, since I have 10 more minutes, and this is really the most exciting part of my talk today. So what I wanted to do next is really just work on some fun graphs. And since we're talking about Julia, I thought maybe a fun graph could be graphs related to Julia. So the first graph we work on is the Julia package ecosystem. And then the second one is Twitter data. So one thing I want to say before we move on is I just wanted to introduce this idea of goods transport. Let me add these two figures here. So if I have figure 1 over here, okay. So I know that the requirements of this class do not, like you don't necessarily know about eigenvalues or spectral analysis or eigenvectors and so on. And the concept I want to run just in a second later now is Pagerank. And because Pagerank has really cool connections to eigenvalues and eigenvectors, I thought maybe the best way I can do this without talking about eigenvectors is kind of try and describe the intuition behind it. And so here, what I wanted to show is the idea of goods transport in a network. So if you take this network over here, A, where you have, I think this is node number 1, 2, 3, 4, and 5, and you build the adjacency matrix of it, and then you build this, essentially it's a stochastic, it's a column stochastic matrix where the sum of each column sums to 1. And the sum of each column sums to 1 because it becomes now a probability distribution. Now the idea is if I start with a vector 3 here, 3 and everything is zeros, what this really intuitively mean, at least in the way I see it without going into the details of eigenvalues, is if I have 3 items here and then I want to run some sort of diffusion on this model, how do these 3 models diffuse? Well, these 3 models are likely to diffuse in the following way. They're going to go to this place, this place, and this place, because they have equal probability distribution to get distributed. And this is where the 1 over 3, 1 over 3, 1 over 3 comes in. Now, the concept of PageRank, what it says is that if I have a network like the network we have over here, and then we have a random person on a network, usually the original concept started with Google, where they wanted to kind of detect where are the interesting pages on the web. The idea was that someone could go from node A to node B with probability alpha and can teleport to some other node with probability 1 minus alpha, given that we start with this matrix, which is a column stochastic matrix. So again, because I don't want to go into the details of eigenvalues and so on, PageRank is a really cool concept that I strongly encourage you to read about or maybe learn about once you know more about eigenvalues. But I really just wanted to hint the concept of it, of what it means to go from just a regular adjacency matrix to a column stochastic matrix. And that's really because that's an easy way to see the probability distributions of how to transfer within a network. Now, I wanted to run PageRank on the two graphs I explained over here. So let's let's do this. If I go to the package ecosystem, all right, there's a bunch of code here that most likely I won't be able to go through all of it or any of it maybe. But really, I do have that data. I'll also, again, all of these links, everything should be easily reproducible. You can download this data and, well, you're not going to download, you could also regenerate the data since you will have Julia installed on your laptop. So whether you download it or regenerate it, both will work. And then we are going to build a network just basically based on the concept if a package requires another package, there's going to be an edge between them. And if not, there won't be an edge between them. And the next thing so we will build the network and we will use the edges based on required packages between them. And then the next thing I wanted to do is to run PageRank. And this is the first PageRank method that I wanted to show you. And it's pretty simple and straightforward. Again, this is not the best way to write PageRank, but a way to write PageRank. So let's actually run some of these while okay, so we're getting the data. Okay, so this function here is really just finding a layout for this graph so that we can be able to visualize it easily. Let me actually see, I think I do have the layout already. Let me see. Yeah, I think this is it. Okay, this is the picture I'm looking for. And I'll go linearly over the code quickly, but here what I'm showing is the top packages that reveal the top PageRank value. And this is really just to convince you that PageRank is a relevant concept that we care about in networks where, for instance, here, the packages that we're seeing make so much sense. So actually, for instance, package is one of them, tests static arrays. I use a lot of linear algebra and I use a lot of sparse arrays. So I'm imagining a lot of packages actually depend on them. So this is just to hopefully convince you that PageRank is a relevant concept, that the PageRank value of a certain node in a graph is relevant in many cases. And I guess this is currently being regenerated, but this is really the PageRank function that we're interested in. Since we are running out of time, I will move on to the next thing, which is the Twitter data, which is actually a really cool case study to show that something about the Julia community, I guess. So the way I'm doing it, I'm not going to rerun these things because they do take, actually scraping the data took about almost a day. But the way we do it is really just via this Python package. It's called Twint. And like, it's super easy to just use it in Julia. All we have to do is, what we really need is this pycall package. Once you have the pycall package, all you have to do is do add py import of the package name, and I keep the package name as twint, that's the package name. And then everything else is like, if you've used this package in Python, you'd be so surprised because this is almost Python code. I guess the only difference is like maybe the upper letter T versus lower letter T for the true. So you get I got all the tweets that have the Julia Lang hashtag and have a minimum likes of 5. And then afterwards, I got the unique usernames who actually have tweeted those tweets and took their usernames. And now I decided I want to build a social network on those unique usernames. And the way we did it is by going over every single username and collecting who they follow. Every time we go over a username, we collect everyone they followed. And now these are the people these people are their friends. And then finally, the last thing we wanted to do is to build the network. And by building the network, every time I grab a new username, I will look at who they follow. And if they follow someone in this list we are interested in, that we are building the network around, we will actually put a yes between them, which is a 1 and 0 otherwise. So the key concept here, for every username, we're getting their file, and then we're getting who they're following, and then we're finding their exact index in the kind of the username list that we have over here. And once we have it, we're just going to populate that person's column. And then the rest of it is really very similar. So we're going to do glance, which is again graph visualization way. And we will visualize all of these nodes. Now, again, in the interest of time, I will stop here and maybe just show the final figure of this result, which is over here. Now, let's see. Okay, so this is it. Okay, so I think what's really cool here is, first of all, there was like a natural kind of clustering of these people over here, which made a lot of sense. Like Kano here, Jeff Bezanson, Chris Rakakis, Viral, Stefan, all of them were in the same cluster, which was awesome, which made sense, right? The visualization algorithm kind of maybe did something interesting there. And David Sanders also, who is on this call, so here he is. And then there were some interesting patterns. For instance, there was like some cluster over here. So I'm interested in, I'll have all of this data for you to play around with it. So maybe this is some cluster of Python users. We don't know, so we'll probably have to find out. And this is Hadley Wickham, who is known in the R community. So maybe these users are actually R community users. So there was a lot of things that were revealed that were interesting in this pattern. And with that, I think I will end here. And I feel really sorry I didn't go into more details and just kind of kept it super brief. But I do have all of the content and data and references in the codes and the everything I've shared with you today. So I will post all of these things online. And I'm happy to, if you ever write me a question about some of this content or the content that I will put online, please feel free to share it with me. And sorry for taking 13 more minutes.
That's great, Huda. I'll applaud for the whole world. I don't know if that
Thank you.
is a real applause, but I'll try my best.
Thank you.
And let me end the stream.